So welcome to part 2 of lecture 14. So I've written up here on the slide what the definition of a polynomial is. And so a function p from the field to itself is a polynomial with coefficients in the field if there exist coefficients a0 up to am such that your function can be written as a0 plus a1 times z plus a2 times z squared all the way up to am to the z to the m. And these functions have shown up in the course. Normally, so far in this course, we've seen them as we're thinking of them as vectors inside of a vector space, but we also want to think of them as functions as well, kind of like the viewpoint that you take in calculus. So one theorem that you have is that if you have a polynomial and it equals 0 for all z and f, okay, so I'm saying as functions. So what does this mean here? This means that every time I plug z into this polynomial, I get the output of z. Then the only way that can happen is if all of these coefficients were 0. So another way of saying this is that there's no polynomial with non-zero coefficients that always equals 0. Okay, so in order to have 0 everywhere, all your coefficients have to be 0. Okay, and things that we've seen already before is we've seen the notion of the degree of a polynomial, right? It's the value m, provided that a to the m is not equal to 0. And if we have the special case where our polynomial is 0, we set the degree of our polynomial to be negative infinity. And we let pf, right, be the set of all polynomials. And what we've seen so far in the course is that this is a vector space. So that's what the polynomial are, and we've seen these before. And probably one of the more important results about polynomials is the division algorithm for polynomials. So I'll first state it. We won't prove it, but I'll state it and I'll show you that you've actually seen this in high school. So suppose that you have two polynomials, p and s, inside of your set of polynomials, and the s polynomial isn't the 0 polynomial. Then there exist unique polynomials q and r, okay, and they're inside of pf, so they're polynomials again, such that p is equal to s times q plus r, where either r is 0 or the degree of r is smaller than the degree of s. And this r here is usually called the remainder. Okay, so r is the remainder after we divide s by p. And it may look kind of a little strange. This may be the first time you've seen it expressed this way, but you have seen this. In high school and in calculus, you've learned how to divide one polynomial by the other. And what this division algorithm statement is saying is that when you do that division, the long form division of polynomials, you will get the q and the r, and you will only get one possible q and r. So let me just kind of show you kind of an example. So let's say my first polynomial is 3z squared plus 2z plus 1, and my second polynomial is 6z squared plus 7z. So we want to find the q and the r, and what we just do is we do long division of polynomials. So we take 6z squared plus 7z, and we want to divide it into the polynomial 3z squared plus 2z plus 1. And remember, what we want to do is we want to say, well, what do I need to multiply this by to cancel out the 3, right? And I think I made a mistake here. Yes, I made a mistake here. I wanted this here to be a cubed, and I want this to be the squared. Okay, so I want this to be the cubed, I want this to be the squared. So I have to ask myself, what do I need to multiply this by to make this? And I have to I want 0z plus 1. So I have the z squared, z cubed, z squared, z, and constant term. So if I multiply this term by 1/2 z, I get 3z cubed plus 7/2 z squared, and I subtract them, right? I subtract these terms, and right here I would get minus 3/2 z squared, and then I bring down my other terms, plus 1, and now I want to cancel off this term, So hopefully this is all looking familiar. And I want to decide, well, what do I need to multiply this by to kill this thing? Well, I need to multiply it by minus 3/12 now in order to make everything cancel properly. So over here, I will get minus 3/2 z squared, and over here I'll have minus 21/12 z. Obviously, I didn't pick this example to have the best numbers, and then I do all the calculations. Oh, this should be over here because this has a z thing. So I'm taking 0z minus 21z, so I end up with 21/12z plus 1. And so to summarize here, what I have is that therefore 3z cubed plus 2z squared plus 1 is equal to 6z squared plus 7z times this element right here, 1/2 z minus 3/12 plus the remainder, plus 21/12 z plus 1. So this element here is the q that's guaranteed by the division algorithm, and this element here is the r, right? And this element is the s, and this is the element, the p. Okay, so that's how what the division algorithm is saying is that you can always find the q and the r, and you would have seen this before either in high school or in calculus. Okay, so I've actually stated this at the bottom. So the division algorithm justifies why there's always a unique solution to this high school problem. So we don't need to do this very often in the course. We're actually just interested more in the fact that there's a theoretical relationship that given any polynomial p and s, you can take the polynomial p, divide it by s, and get something smaller, the remainder, which is smaller than the thing that you started with. So we'll see actually using the division algorithm in the next part where we talk about roots. So I'll see you in part 3 of today's lecture.